Hi, my name is Joseph Muhammad Ali, and today we'll be doing experiment number 9, which is Equilibria of buffers. The objective of this experiment was to prepare and understand characteristics of buffer solutions. Let's get started. In this experiment, we calculated the pH of sodium acetate and acetic acid after the addition of hydrochloric acid. I will discuss the calculations after this. First, I will describe what the definition of pH is and give some examples. pH is a scale which is used to specify how acidic or basic a solution is. Acidic solutions have a lower pH, therefore are lower on the scale, and basic solutions have a higher pH and are therefore higher on the scale. I have some household items that have several pHs. So this is regular water. This has a pH of 7, so it is considered neutral. This is baking soda. It has a pH between 8 to 9, but it's considered 8.4. This is borax. It has a pH of 9.3, so it's very basic. This is white distilled vinegar. It has a pH of 3, so it's very acidic. And I have some lemon juice, which has a pH of 2.9 to 3.2, so it's also very acidic. Next, I will talk about buffers. A buffer is an aqueous solution consisting of a mixture of a weak acid and its conjugate base. So as we see in this experiment between the acetic acid and the sodium acetate, that creates an equilibrium, and it buffers out so the pH stays closer to the original pH if you add acid or base. An example of this in the human body would be our blood. It is at a pH level of 7. There's a lot of carbonic acid in our blood, which is a weak acid, and its conjugate base is bicarbonate, and together they maintain the blood at the pH of 7.4. In this experiment, we were given 4 different amounts of hydrochloric acid to put into the buffer system to see how much the pH would change or be affected. So for the first trial, we were given 0.5 milliliters of hydrochloric acid, and we converted this to liters, which give us 0.0005 liters of hydrochloric acid. Next, we needed to convert the hydrochloric acid liters into moles. So we took the 0.005 liters and used this equation to convert it to moles. Once we have the moles of the hydrochloric acid, we can add that 0.055 moles to the 0.20 moles, which was the combination of the acetic acid and the sodium acetate. That was the combination in their moles. So for the acetic acid, you add the 0.005 moles, and for sodium acetate, you subtract the 0.0005 moles of hydrochloric acid. And we get the following values: 0.0205 moles of acetic acid and 0.0195 moles of sodium acetate. Once you get those values, you can plug it into this setup. So the top represents the moles of the product, which was the numbers that we just solved for, and the bottom is the amount of the solution. So you simply divide these two numbers, and this gives you the molarity, the molarity of the solution. So once you divide the 0.0205 moles of acetic acid by the 0.205 liters solution, you get 0.001 molar of acetic acid. And you repeat the same steps for sodium acetate. You divide the 0.0195 moles of sodium acetate by the 0.0205 liters of solution, and this gives you 0.00095 molar sodium acetate. Next, you use this equation. It helps us to determine the pH. This value, the 4.76, is the pKa of acetic acid, and it is a given value, and it is a constant. Once we plug the 0.0095 molar and the 0.01 molar of acetic acid and sodium acetate into the equation, we're given 0.95. And then once we take the log of that, we're given 4.76 plus negative 0.0223. Once you add those two together, you get the pH of 4.738. And this shows how the buffer system works. It shows that it didn't change much even with the addition of a really strong acid, hydrochloric acid. And the same thing goes for the other amounts. So when we added 20 drops or 1 milliliter of hydrochloric acid, you can see it didn't change very much, only by a little amount. And the same goes for the 30 drops and the 40 drops. It changed in very small amounts. That just shows how a buffer system really works.